Red dwarfs. These are the most common and longest-lived stars in the entire universe, making up the vast majority of the stellar population in our own Milky Way galaxy. Despite their incredibly abundance, you cannot see a single one of them with the naked eye from Earth because they are incredibly small and dim, burning their nuclear fuel at a remarkably slow and efficient pace. They are roughly a fraction of the size and mass of our Sun, which means their internal temperatures and pressures are much lower, preventing them from shining with the fierce intensity of larger stars. Because they consume their hydrogen supply so conservatively, a typical red dwarf can continue to burn steadily for trillions of years, far longer than the current age of the universe itself. This incredibly long lifespan makes them a major focus for astronomers searching for habitable exoplanets, as any world orbiting closely enough within their habitable zone would have billions of years of stable conditions for life to potentially develop. However, their tendency to unleash violent magnetic flares in their early years presents a significant challenge for the survival of any atmospheres on those nearby planets.
Yellow dwarfs. This is the category of star that includes our very own Sun, serving as the cosmic anchor for our solar system and the ultimate source of life on Earth. Despite the name, they actually appear brilliant white when viewed from space, only taking on a yellowish hue when their light is scattered by a planetary atmosphere like ours. They are medium-sized main-sequence stars that spend roughly 10 billion years of their lives steadily converting hydrogen into helium at their superheated cores. This stable, reliable output of energy provides the perfect, consistent environment needed for complex life to evolve over eons on surrounding planets. Throughout this long middle-age phase of their life cycle, they maintain a delicate balance between the inward crushing force of their own immense gravity and the outward explosive pressure generated by their continuous nuclear fusion. Eventually, after billions of years of shining, they will exhaust their primary hydrogen fuel reserves, which drastically alters their internal structure and forces them to expand outward, swallowing their innermost planets as they transition into the next dramatic phase of stellar evolution.
Blue giants. These are the massive, incredibly luminous rock stars of the cosmos, burning with a ferocious intensity that makes them stand out brilliantly against the dark backdrop of space. They are significantly larger and much hotter than our Sun, containing enough mass to create crushing internal pressures that drive their nuclear fusion at a terrifyingly rapid pace. Because their surface temperatures are so extreme, peaking at tens of thousands of degrees, they emit most of their energy in the blue and ultraviolet spectrum, giving them their signature piercing color. This reckless consumption of hydrogen means they live fast and die young on a cosmic timescale, exhausting their enormous fuel supplies in just a few million years, rather than the billions enjoyed by smaller, calmer stars. You will often find them clustered together in active star-forming regions like the Orion Nebula, illuminating the surrounding clouds of gas and dust with their fierce radiation. Their incredibly short lifespans guarantee that they will ultimately meet a violent and spectacular end, self-destructing in cataclysmic explosions that forge the heavy elements necessary for building future planets and moons. Red giants. This represents the spectacular and destructive late-stage evolution of an average-sized star after it has completely depleted the hydrogen fuel in its core. When the fusion engine at the center finally shuts down, the core begins to collapse under its own gravity, generating intense heat that ignites a thin shell of remaining hydrogen just outside the center. This sudden surge of new energy forces the star's outer layers to expand massively, swelling to hundreds of times its original size and engulfing any inner planets unfortunate enough to be in the way. As these outer layers stretch further away from the central heat source, they gradually cool down, shifting the star's emitted light from a brilliant white or yellow to a deep, ominous red.
Our own sun is destined to become one of these swelling monsters in about 5 billion years, eventually growing large enough to swallow Mercury, Venus, and very likely Earth. During this bloated phase, the star sheds vast amounts of its outer material into deep space through powerful solar winds, seeding the galaxy with the raw chemical ingredients needed to form entirely new solar systems in the distant future.
Red supergiants. These are the absolute titans of the universe, representing the absolute largest stars in existence in terms of sheer physical volume, dwarfing almost everything else in the night sky. They form when massive stars, much heavier than our sun, run out of their primary hydrogen fuel and begin to expand uncontrollably, swelling to proportions that defy human comprehension. If you were to place one of these colossal spheres at the center of our solar system, its outer edges would stretch well past the orbit of Jupiter, completely obliterating the inner planets. Despite their unimaginable size, their outer layers are actually quite cool and incredibly diffuse, almost like a glowing red-hot vacuum. Deep within their core, however, extreme gravitational pressures allow them to fuse increasingly heavy elements, burning through helium, carbon, oxygen, and silicon in a desperate bid to stave off collapse. This heavy element factory continues until the star attempts to fuse iron, a process that absorbs energy rather than releasing it, instantly triggering a catastrophic structural failure that inevitably leads to one of the most powerful explosions known to modern astronomy. White dwarfs. These are the dense, glowing embers left behind after an average-sized star has exhausted all its nuclear fuel and violently shed its outer layers into the surrounding cosmos. What remains is the exposed, dead core of the star, roughly the size of the Earth, but containing a mass comparable to the Sun, making it one of the densest forms of matter in the universe. A single teaspoon of material gathered from its surface would weigh several tons, held together by bizarre quantum mechanical forces that prevent the dead star from collapsing any further under its own immense weight. They no longer generate new energy through fusion. Instead, they shine purely from the residual, trapped heat left over from their active lifespan, glowing with a brilliant, ghostly white light. Because they are so small and incredibly dense, they cool down at an agonizingly slow rate, taking tens of billions of years to slowly fade into complete darkness. Eventually, when all their thermal energy has finally radiated away into the freezing void, they will theoretically become cold, black, crystalline spheres, silent monuments to the fiery stars they once were billions of years ago.
Neutron stars. These are the extreme, hyper-dense remnants forged in the devastating aftermath of a supernova explosion, born when a massive star completely collapses under its own crushing gravity. The inward pressure during this collapse is so incredibly violent that it forces electrons and protons to smash together, merging them into a solid, city-sized sphere composed almost entirely of tightly packed neutrons. The density of this object is nearly incomprehensible. A piece the size of a sugar cube would weigh hundreds of millions of tons on Earth, equivalent to the mass of a large mountain. Because they inherit the angular momentum of the original, much larger star, they spin at dizzying speeds, sometimes completing hundreds of full rotations every single second. Many of them possess terrifyingly strong magnetic fields, trillions of times more powerful than Earth's, which channel beams of intense radiation out of their magnetic poles. As they spin, these beams sweep across the cosmos like a lighthouse.
Brown dwarfs. These are the strange, mysterious misfits of the cosmos, often referred to as failed stars, because they occupy the gray area between the heaviest gas giant planets and the lightest true stars. They form from collapsing clouds of gas and dust, just like any other stellar object,
but they simply do not gather enough mass to generate the extreme core temperatures required to ignite sustained hydrogen fusion. Without that internal nuclear engine, they cannot shine with the bright, steady light of a true star, leaving them to glow faintly in the infrared spectrum through the slow release of heat left over from their initial formation. Because they are so incredibly dim and cool, they are notoriously difficult for astronomers to detect, often requiring highly sensitive infrared telescopes to spot them lurking in the dark interstellar neighborhoods. They possess complex, turbulent atmospheres that behave more like the violent weather systems found on Jupiter, complete with swirling clouds composed of hot iron and silicate minerals. Studying these objects provides a crucial missing link, helping scientists understand the exact boundary where a massive planet ends and a functioning stellar furnace begins.